We're going to start with these three equations that we just derived in the previous video. And again, as a refresher, we have the force component in the x direction, in the y direction, and the z direction in the first frame of reference. In terms of the force components x, y, z in the second frame of reference. So that is our starting point. Now what we're going to do is the goal of our derivation, which is to find how the electromagnetic force transforms under a relativistic transformation. And we're going to start with the motivation that we're looking at the electric field. Think of it like you have an accelerator, and then at the end of the accelerator you have two, say, electrons flying across. And you're standing right here in the laboratory frame of reference, and you see these two electrons flying across. So then if you were to ride with the electrons, you would just notice the electric field. The question is, will the observer in the laboratory frame of reference also see these relativistic electrons moving close to the speed of light as only experiencing an electric field, or will something else come up? We will see that it's actually the magnetic field that is observed in the laboratory frame of reference. So, having said that, let's go ahead and start. As before, we start with our frame of reference, x, y, z, here in the black, x1, y1, z1, and we have now our frame of reference under constant velocity, x2, y2, z2. Here, and by the way, we have the streamers again, showing that this one is moving with a velocity v, which is a scalar, in the direction I. Now here what we're going to have is we're going to have two particles, here and here. And these two particles are going to be charged. One is going to be Q sub A, and this one is going to be Q sub B. And they're going to have an electric field in the second frame of reference. What are they going to see in the first frame of reference is the question that we seem to want to know. What we're going to say then is that, first of all, there is no z component because both of these particles are in the xy plane here. So the z component is 0. Now, in frame 2, the force on Q sub B is F sub B2. Okay, and like before, that's going to be an x component, y component, and z component. So let's go ahead and, we have x, y, and z, k hat, j hat, I hat. So let's go ahead and concentrate on x sub B2. That's going to be equal to, of course, charge A, charge B, x sub 2, which is this guy, divided by 4 pi epsilon naught times r sub 2 cubed. Now, this is Coulomb's law considering the vector nature of x sub 2 and r sub 2. Similarly, we're going to have y sub b2 equal to pretty much something very similar. Four pi epsilon naught r sub 2 cubed. Now, just for completeness sake, we're going to have the z component, and that one is going to be equal to 0. Why? Because again, we are looking only in the xy plane. These two charges are pasted against this wall back here. Fair enough. Now let's calculate the force on QB from the other frame of reference. So here, what we have from our previous equations is x sub 1 is equal to x sub 2 plus all of these things. But remember that in this frame of reference here, our velocity 2y is equal to 0. And that is also equal to velocity 2z. So 2z and 2y are equal to 0. And what else? Actually, this is also v sub 2x. In other words, the velocity in the x, y, and z directions of particle A and particle B, for that matter, are 0 in that frame of reference. The entire frame of reference is definitely moving at velocity v, but the relative velocities in this frame of reference are 0. So that has a major impact on our equations. x1 equals to x2 plus this times this product, but since this is 0, that entire term goes to 0. Similarly, y sub 1 equals to y sub 2 over only gamma, because v sub 2x goes to 0. So those guys going to 0 does simplify our equations. We're not going to worry about z. Specifically, what we have is x sub b1 equals to x sub b2, and y sub b1 equals to y sub b2 over gamma. Why over gamma? Because of this equation right here. That term goes to 0, but gamma is still multiplying a 1 here. So we end up with y sub 2 over gamma. Okay, so I guess for completeness sake, we can say zb1 equals to 0. First of all, we go ahead and write x sub b1 equals to x sub b2, which after we drop off the one subscript becomes x sub b is equal to gamma times qa qb little x over our traditional denominator, 4 pi epsilon naught gamma squared x squared plus y squared to the 3/2. Similarly, we can go ahead and write the y equation, the y component. Y sub b1 is equal to y sub b2 over gamma. That is a gamma down there, which implies, again, after we drop off the one subscript, we can go ahead and say then that is qa qby over our traditional denominator and 1 over gamma here. Now, the next thing we're going to do here is we're going to go ahead and write our gamma in a particular way. In other words, it's 1 over gamma, but we're going to write it as gamma over gamma squared, which is equivalent to saying gamma times this quantity without the square root, 1 minus v squared over c squared. So once we have that written, we end up with this equation for y. We see gamma qa qb from here, y, and our traditional denominator, and then this 1 over gamma then, remember, has been absorbed into gamma times this 1 minus v squared over c squared. So far so good. Now we're going to go ahead then and write the following. We're going to say that f sub b, which now combines both components, is going to be equal to gamma qa qb times the vector r that now has absorbed one of these x's, and this y right here from the y sub b component has been absorbed into this r vector here. And then that is going to be subtracted. From that, we're going to subtract gamma qa qb y v squared j hat. And that is going to be almost the same denominator as before, except that this one is going to have a 4 pi epsilon naught c squared times gamma squared x squared plus y squared to the 3/2. And here we're also going to have the same denominator, but without this c squared here, and that's going to be gamma squared x squared plus y squared to the 3/2. Okay, now we can factor out gamma qa qb and a bunch of this other stuff down in denominator. So we'll say gamma qa qb over 4 pi epsilon 0 times gamma squared x squared plus y squared to the 3/2. And here what we're going to have then is we're going to have this r right here. So that's vector r minus v squared over c squared times y times j hat. So what we're going to do now is we're going to write down this minus j hat minus v j hat as v cross k. So we're going to show that in the next step, and after that then we will be able to substitute this into this term right here. So what we're going to show then is that this cross product right here is going to yield something interesting. Specifically, we do that by saying I, j, k, and v sub x, v sub y, v sub c, 0, 0, 1. So take the determinant of that, and that's going to give us I times v sub y plus, minus j hat v sub x plus k hat times 0. So here what we can easily say is that goes to 0. And let me make an argument that v sub y is also 0. Because if you remember, what we showed at the very beginning was that our frame of reference was this, our x sub 2 frame of reference. So what we're seeing is that there's no velocity in the y direction, there's no velocity in the z direction, but there is a velocity v in the x direction. So v sub x is non-zero, but the other ones are 0 because the frame of reference is only being thrust in this direction where the streamers are showing. So if that's the case, v sub y is equal to 0. This entire term goes to 0. So what we're left with here is minus j hat v sub x, or in this case v, really. F sub b equals to q sub b, where we factored out the q sub b, times curly brackets gamma qa vector r over 4 pi epsilon naught times our usual friend here, plus, now we can use the v cross k expression. So we go ahead and put brackets vector v cross a bunch of constants, gamma q sub a, y, k hat v. And that's where that k hat v is being put in, 4 pi epsilon naught c squared times gamma squared x squared plus y squared to the 3/2. And we close these brackets and close the curly brackets. So what we're having here is something interesting. We have the electric field term right here, but we have a v cross something right here. So let's write it in a form that maybe we're more used to seeing this in. F sub b equals to q sub b times E sub a, where E is the electric field vector, plus velocity cross B sub a. B sub a, which we're defining as the magnetic field. And we can then say where E sub a, electric field vector, is equal to gamma q sub a r And hopefully this will be the penultimate time we write this expression down. Gamma squared x squared plus y squared to the 3/2. And then here enters our magnetic field, equals to gamma q sub a y and k and v divided by 4 pi, and we have epsilon naught c squared times, hopefully this is the last time we write this friend down, gamma x quantity squared plus y squared to the 3/2. So that is exactly where the magnetic field is coming in. We're coming up with a Lorentz force derivation that forces us to have this term B right here. And the first term, of course, is seen to be the electric field with a gamma put in, which makes sense because it's been relativistically transformed. But this has come out in the wash. So these are our final expressions. This one here is for the Lorentz force, which shows the electric field and the magnetic field. And this is actually the first place where the magnetic induction is making its debut. It's showing up. Purely based on a force transformation of special relativity. So that was interesting. I mean, we essentially just did a force transformation, and out of that comes this weird term that we're baptizing as magnetic induction. So that is indeed where the magnetic field comes from, the mathematics of special relativity force transformations. I hope this was interesting and useful.